Hello, continuing with section 7.2, we look at the last few examples. There are two examples. So, example 3, evaluate each expression under the given condition. So, here we are asked to evaluate this expression sine of theta plus phi. Now, if you recall these sine of theta plus phi, sine of theta minus phi, cosine of theta plus phi, cosine of theta minus phi. So these four formulas kind of we learned, which are, we call them sum or difference formulas, and they involve the sine function and the cosine function of the angle, not the rest of the trig ratios or trig function values. So our goal is to get or find the sine of theta and cosine of theta and sine of phi and cosine of phi. If some information is given, good, but we have to find the other which is not available. So we start with the first here. So we are given this information about theta, that cosine of theta is 12 over 13 and theta is in the quadrant 4. So I am using the triangle method here. So I drew a triangle in the fourth quadrant here. In the fourth quadrant, I have the triangle. You can see that. So theta is the angle, little angle with the x-axis. And then we have the cosine of theta is adjacent over hypotenuse. So I put the 12 over along the x-axis. The side of the triangle is 12 and the hypotenuse is 13. So now we have this side vertical, which we need to figure out. And how do we find it? Using the Pythagorean theorem. So I called it B, and now I'm finding B over here using again the Pythagorean theorem, and then we are getting B is equal to plus minus 5. But what will B be? Because we are in the fourth quadrant, and in the fourth quadrant sine is negative. The y coordinate is also negative. So this represents the y coordinate. So we have a b is equal to negative 5. So once we got all three sides of the triangle, now we can write any trig ratio or trig function value. So cosine of theta was given, so I needed sine of theta, so I wrote sine of theta, which will be now negative 5 over 13. In the same way, now we go to the other angle, which is phi, and we are given the information that the sine of phi is equal to negative 4 over 5, and phi is in the third quadrant. So I drew the phi in the third quadrant over here. This is phi, and sine is negative 4 over 5. So sine is opposite over hypotenuse. There is a negative sign, since the hypotenuse can never be negative. The negative negative will go with the 4, which is our opposite side, and then 5 goes with the hypotenuse. And now we have that third side left, which we don't know, so we call it A, and then I use the Pythagorean theorem, find A. Now will A be negative or positive? Well, because A is along the negative x-axis, so A will be negative. Or you can say, because our triangle is in the third quadrant, therefore both sides will be negative. Both legs, along the legs, we will put a negative sign. Now we can find cosine and sine. Sine is already given, so cosine will be negative 4 over 5. Now that we have this information, now we can figure out what is sine of theta minus phi plus phi. So it will be sine theta cosine phi plus cosine theta sine phi. Now I plug in the values and just multiply. Now notice here, and this here in the first expression, we can cancel this 5, but then we won't be able to put it together. In order to put it together, we will have to again multiply by the 5 top and bottom in order to make the denominator same. So that's why I am not cancelling it, just keeping it as it is. So I get 15 over 65 minus 48 over 65, which gives me negative 33 over 65. Now the next example is very similar. Here I have shown it to you by using the trig identities instead. Actually, identities are taking longer than they take longer than the triangle method, but it's your choice whatever method you use. So here we have to find this expression, cosine of theta minus phi, and we are given sine of theta is 2 over 3 and theta is in quadrant 2. So you can again draw the triangle, use the triangle method if you want, but if you want to use the identities, then we know that cosine square theta plus sine square theta is equal to 1, or cosine square theta is equal to 1 minus sine square theta. So that's what I am doing here. Sine of theta is 2 over 3. So cosine square theta is 1 minus sine square theta, or 1 minus 4 over 9, which 1 minus 4 over 9 gives me 5 over 9, and 5 over 9 means cosine square is 5 over 9. So cosine of theta will be plus minus square root of 5 over 3, but we are in the second quadrant, so cosine of theta will be negative of square root of 5 over 3. Okay. The other angle information given is tangent of phi. So tangent of phi is equal to square root of 7. So, and phi is in quadrant 1. So every, remember in quadrant 1, all trig functions are positive. Okay, so when we have this information about tangent, we cannot directly find sine and cosine. We have to first find secant, because the Pythagorean, using the Pythagorean identity, one of the Pythagorean identity, which is, remember the 3 Pythagorean identities are that cosine square theta plus sine square theta is equal to 1, and the next one is 1 plus tangent square theta is equal to secant square theta. And the third one is 1 plus cotangent square theta, or cotangent square theta plus 1, the same thing. Is equal to cosecant square theta. So using the second identity, there I have secant square theta is equal to, secant square phi is equal to 1 plus tangent square phi which is equal to 1 plus 7, which gives me 8 as the answer. So secant of e will be plus minus square root of 8, but since we are in the first quadrant, secant of e will be square root of 8, which is 2 into square root of 2. And now you can find the cosine, which will be 1 over square root of 8. So simplify it, rationalize it, you end up getting cosine of phi is equal to square root of 2 over 4. And now we can find sine by using the first Pythagorean identity. So sine squared phi will be 1 minus cosine squared phi. Plug in, end up getting 7 over 8. Cosine squared is 7 over 8. So cosine will be square root of 7 over square root of 8. And then rationalize the denominator and we get square root of 14 over 4. That is our cosine phi. So now we are going to find out what is our required quantity equal to. So we have cosine of theta minus phi, so which is cosine theta cosine phi plus sine theta sine phi. Plug in the values and we end up getting this as our result. So you should be able to do this problem with the triangle method and see that you should get the same answer. Okay, the next example 4 is saying verify the identities. Now we are going to verify these identities, but they are special identities. They are actually some formulas. And so the first one is saying show that or verify that sine 2x is equal to 2 times sine x times cosine x. So now what is this thing? Well, if you notice 2x is double of x. So that's why this is called the double formula. Okay, so this is double formula for sine x. Double angle formula. Double angle formula means if we have double the angle, how do we get that? So how can we show it? How can we prove it? Well, think outside the box. With 2 times x can be written as x plus x. So sine of 2x can be written as sine of x plus x. And now if we apply the sum formula of the sine on this, then we get sine x times cosine y, but y is again x here again. So I get sine x times cosine x plus cosine x times sine y, but y is the same as x. So I go sine x again. Now both these terms are same. The sine x cosine x and cosine x sine x. So both are same. So we can write them as is equal to 2 times sine x cosine x, which is our right hand side, which is what we wanted to prove. So this is sine of 2x is equal to 2 sine x cosine x. You have to kind of again remember, but if you do not remember, you should know how to get it. So if you are given sine 2x, you can write it like sine of x plus x and apply the sum formula. Okay, the next one is, so this is the double angle formula for sine, and now we will see the double angle formula for cosine. So cosine of 2x is equal to cosine square x minus sine square x equals to 1 minus 2 sine square x equals to 2 cosine square x minus 1. So all these are equal to each other. So basically what has happened here is a bunch of identities, you can say. So we will split it. We will show that cosine of 2x is equal to cosine square minus sine square. Then we will show that cosine of 2x is equal to this quantity 1 minus 2 sine square x, and then we will show that cosine of 2x is equal to that one. So here I split them as 1, 2, and 3. So for the first one, we do it the same way we did in the previous uh, formula for sine. So I will write cosine 2x as cosine of x plus x and apply the sum formula. So according to the sum formula, I have cosine x times cosine x minus sine x times sine x, which is cosine square x minus sine square x, and which is our right hand side. So we have shown that cosine of 2x is cosine square x minus sine square x. Now you have to be careful about it. You cannot change them. Note that the Pythagorean identity sine square x plus cosine square x is equal to 1. We can write it as cosine square x plus sine square x equals 1. But here with the formula we cannot switch them. We cannot do sine square minus cosine square. It has to be cosine square minus sine square. Okay, so the first one is done, shown. Now let's show the second one. Now for the second one, I will actually start at this level. We know that cosine of 2x is equal to 1 is equal to cosine square x minus sine square x. We are here. So we from the previous one we are here. So cosine 2x is cosine square x minus sine square x. I can say. Now I want to show that this quantity actually gives me that. So if you compare these two, this is cosine square x minus sine square x. So it means it has both cosine square and sine square. But this expression has only sine square. So what does that kind of give you a hint or tell you? It says get rid of this cosine square. How can we get rid? We can apply or use Pythagorean identity. So cosine square is equal to 1 minus sine square. So I replace the cosine square by 1 minus sine square, and then I have already minus sine square there. This open the parentheses, collect the like terms, we get 1 minus 2 sine square x. So we have shown our identity is true. The third one, we do it this similar way as the second. So cosine of 2x, I will start here with cosine square x minus sine square x. But I want to get 2 cosine square x minus 1, which means I want to get rid of the sine square. So what will I do? I will replace the sine square by 1 minus cosine square. And so combine the like term, we end up getting 2 cosine square x minus 1. So what this means is that there is one for double angle formula for sine, but there are 3 double angle formulas for cosine. So cosine of 2x is same as cosine square x minus sine square x, and cosine of 2x is the same as 2 cosine square x minus 1, and cosine 2x is same as 1 minus 2 sine square x. Now if you do not remember this, it's fine, it's not a big deal, but you should know how to get it. So if you are given cosine 2x, the instinct should tell you to split it as x plus x and then go from there. Okay, so this is what you should know from section 7.2.